Distribution is the process by which a drug moves from the bloodstream into different tissues and body fluids after being absorbed. In simple terms, once the drug enters the blood, it gets distributed throughout the body to reach its sites of action, storage areas, or elimination. The extent and rate of this process depend on the drug's properties and the physiology of the patient. Imagine the bloodstream as a delivery van that carries packages, that is drugs, to different houses, that is organs. Some organs, such as the liver, kidneys, and brain, receive the drug quickly because they have a rich blood supply, while others, like fat, skin, or muscle, receive it more slowly. A portion of the drug remains in the blood, plasma, while the rest is delivered to various tissues. This overall process is known as distribution. The apparent volume of distribution, VD, is a theoretical concept that describes how extensively a drug is distributed in the body relative to the plasma concentration. It is called apparent because the value obtained does not represent a real physical volume in the body but rather a theoretical one. The body does not have a single uniform space where the drug distributes evenly. Instead, different drugs distribute unevenly between plasma, tissues, and fat. The calculated VD is therefore only an apparent or assumed volume that reflects how the plasma concentration of a drug relates to the total amount of drug in the body. For example, if you administer 100 milligrams of a drug intravenously and measure a plasma concentration of 10 milligrams per liter, the VD would be 10 liters. This 10 liters does not mean that there is a literal 10-liter compartment in the body. It simply means that the drug behaves as if it were evenly distributed in 10 liters of fluid to produce that concentration. Some drugs show a low VD, smaller than total body water, meaning they remain mostly in plasma, example heparin, warfarin, while others have an extremely large VD, even over 100 liters, indicating that they are highly tissue-bound and only small amounts stay in plasma, example chloroquine, digoxin. Thus, it is called apparent because it does not represent an actual physical volume but a mathematical reflection of how widely a drug appears to be distributed. The apparent volume of distribution is calculated by dividing the amount of drug present in the body by the plasma concentration of the drug. In other words, it provides an idea of whether a drug mainly stays in the bloodstream or diffuses widely into tissues. If a drug remains confined to the plasma, it will have a low VD, while if it moves extensively into tissues, the VD will be large. For example, a drug like heparin stays mostly in the plasma and has a low volume of distribution, whereas chloroquine and digoxin enter tissues extensively and have a high VD. Clinically, this concept helps in calculating the loading dose of a drug using the formula. Loading dose is equal to VD into desired plasma concentration. Therefore, drugs with a high VD require a larger loading dose to reach effective plasma levels. The factors affecting drug distribution can be easily remembered using the mnemonic "Please let the blood flow deeply." Here, P stands for physico-chemical properties such as molecular size, ionization, and pH, which determine how easily a drug crosses membranes. L stands for lipid solubility. Drugs that are more lipid-soluble penetrate tissues better and therefore have a higher VD. T represents tissue binding. Drugs that strongly bind to tissues get stored there and remain longer in the body, increasing their apparent volume of distribution. B refers to blood flow. Highly perfused organs like the liver, kidneys, and brain receive the drug faster, while poorly perfused tissues like fat and muscle receive it more slowly. F stands for fat and fluid distribution. Conditions such as obesity, edema, or dehydration can alter the proportion of fat and water in the body and affect how drugs distribute. Finally, D stands for disease states. Disorders such as liver or kidney disease, or conditions causing low plasma proteins, like hypoproteinemia, can change protein binding and fluid volumes, thereby altering distribution. As drugs also differ in their extent of distribution depending on their physico-chemical properties, plasma protein binding, and lipid solubility. The volume of distribution, VD, reflects how extensively a drug spreads from the plasma into body tissues. Drugs with a low volume of distribution are those that remain mainly in the plasma or extracellular fluid and do not penetrate tissues effectively. These drugs are usually hydrophilic, large in molecular size, or highly plasma protein bound. An easy way to remember them is by using the mnemonic stays in the plasma. This stands for S-sulfonamides, T-tobramycin, aminoglycosides such as gentamicin, Y-warfarin, which stays in plasma due to strong protein binding, and S-heparin, a large, charged molecule confined to the bloodstream. Such drugs have limited distribution because they cannot easily cross lipid membranes, so their VD values are small. Therefore, they are often found mostly within the intravascular compartment, making them suitable for conditions where a localized plasma effect is desired. In contrast, drugs with a high volume of distribution spread extensively into tissues, fat, and organs, leading to low plasma concentrations. These drugs are generally lipophilic, small, and unionized, which allows them to cross cell membranes easily. The mnemonic, charming drugs penetrate deep, helps recall these examples. C stands for chloroquine, which is stored extensively in organs such as the liver and spleen. D stands for digoxin, which binds strongly to cardiac and skeletal muscle. P stands for propranolol, a highly lipophilic drug that penetrates tissues deeply, and D stands for diazepam, which distributes widely into fat and brain tissues. Because these drugs accumulate in tissues, their apparent volume of distribution is large, and they often have longer half-lives. This property also means that drugs with a high VD require larger loading doses to achieve the desired plasma concentration. In summary, distribution determines where a drug travels in the body, while the apparent volume of distribution quantifies this spread only theoretically. Several factors, including physico-chemical properties, lipid solubility, tissue binding, blood flow, body composition, and disease states, collectively influence how much and how fast a drug moves from blood to tissues. The mnemonics for factors affecting drug distribution: please let the blood flow deeply. For drugs with low volume of distribution, stays in the plasma, and high volume of distribution, charming drugs penetrate deep, provide simple and effective ways to recall the key principles and examples of drug distribution.